We saw in the first video that if we want to understand irreducible elements in Z adjoin I, it's enough to understand which primes can be written as a sum of two integer squares. So when presented with a question like this, my first instinct is usually to just write down a bunch of examples and see if you can guess what the right answer should be. So, okay, which primes can be written as a sum of two integer squares? 2 is 1 squared plus 1 squared, so that's good. 3, well, the squares are 0, 1, 4, 9, and I don't want to use any 4s or 9s or 16s or whatever. So there's just no way to add up two integer squares to get 3. So, okay, not possible. 5 is 1 squared plus 2 squared. 7, again, if I just add up a bunch of 0s, 1s, 4s, 9s, 16s, there's no way to pick 2 of them and get to 7. Same problem, 11. 13 is 2 squared plus 3 squared. 17 is 1 squared plus 4 squared. 19 I can't do. And you could go on, but hopefully if you stare at this list, you'll be able to guess what the right answer is. So I want to tell you part of that right answer now. So suppose that we do have p equals a squared plus b squared, where a and b are integers. You can take both sides of this equation and reduce modulo 4. What I mean is there is this natural projection homomorphism from Z to Z mod 4Z. And whatever the equivalence class of P mod 4 is must be the same as the equivalence class of a squared plus b squared modulo 4. So what does that give us? This gives us an equation in Z mod 4Z, P equals a squared plus b squared. So this is one instance of this general idea about solving polynomial equations that is talked about in the textbook a little bit in this section called the reduction homomorphism that's in section 7.3, page 245 to 246. I recommend that you check this out. Okay, well, a squared plus b squared in Z mod 4Z. We can just choose representatives for the elements of Z mod 4Z, say 0, 1, 2, 3, and square each one of them and see that 0 squared is 0, 1 squared is 1, 2 squared is the integer 4, which is 0 in Z mod 4Z. 3 squared is the integer 9, which is in the same class as 1 modulo 4. This is 1 in Z mod 4Z. So what are the squares in Z mod 4Z? They're just 0 and 1. And okay, that means if you're adding up a squared plus b squared in Z mod 4Z, what could you get? You could get 0 plus 0, 1 plus 0, 0 plus 1, or 1 plus 1. But all you're going to get is 0, 1, and 2. So what does that mean? If P is equivalent to 3 modulo 4, there's no way that you could have started with P equals a squared plus b squared, because then when you reduce modulo 4, you're getting something that's impossible. You're seeing that 3 is equal to a sum of 2 squares in Z mod 4Z, and that's just not possible. Okay, so that's one direction here. If P is a prime with P equivalent to 3 modulo 4, then P equals a squared plus b squared has no integer solutions. So let's look back up here. 3, 7, 11, 19, primes that are equivalent to 3 modulo 4, you can't write any of them as a sum of 2 squares in Z because you can't even write them as a sum of 2 squares in Z mod 4Z. So this is a really powerful idea in number theory. If you want to solve equations in the integers, you certainly would be able to solve them in Z mod NZ for different choices of n. So one way to show that there are no integer solutions to some equation is to show that there are no integer solutions modulo n for some cleverly chosen choice of n. Okay, so in this case, P is not a sum of 2 integer squares. And from what we've seen before, that means that P is irreducible as an element in Z adjoin I. So what about the other primes? Well, 2 is a sum of 2 squares. Great. That means that 2 factors into a product of 2 irreducibles in Z adjoin I. Well, what about all the other primes? All the other primes are the primes that are congruent to 1 modulo 4. And we will see at the end of this lecture that if P is a prime that's equivalent to 1 modulo 4, then P equals a squared plus b squared does have an integer solution. And that means that P factors as a product of exactly two irreducibles, P equals a plus bi times a minus bi in Z adjoin I. Okay, so I'll pause and erase. And instead of jumping right into the proof of this proposition, I'm going to state a more general result that completely characterizes which n are the sum of two squares, how many times, and then exactly what the irreducibles are in Z adjoin I. All right, let's state the big theorem of this part of section 8.3, which is proposition 18. The first part is Fermat's theorem on the sum of two squares. And this characterizes exactly when a prime can be written as a sum of two integer squares. The prime P is a sum of two integer squares, P equals a squared plus b squared for some a, b, and z, if and only if P equals 2 or P is congruent to 1 modulo 4. We've actually already seen this in the sense that, okay, 2 is a sum of two squares. We've seen that no prime congruent to 3 mod 4 is a sum of two squares. And we just stated this proposition that said that any prime congruent to 1 mod 4 is a sum of two squares. Okay, so that is what we still need to prove, just that last part. And except for interchanging a or b, or changing the signs of a and b, the representation of P as a sum of two squares is unique. And that is something that we've already proven. So we proved before that P factors as a product of two irreducible factors in Z adjoin I, if and only if P can be written as a sum of two squares. But we also showed that in the case that P did factor and P was the sum of two squares, that representation was unique up to switching a and b or changing the signs of a and b. And that followed directly from the fact that Z adjoin I is a UFD. So the factorization of P into that product of two irreducibles is unique up to choosing different associates for those two irreducibles such that the product is still exactly P and not some other unit times P. Okay, so we just have one more piece to prove here, which is we need to show that if you have a prime that's 1 mod 4, it is a sum of two squares. This statement is very closely related to the characterization of all the irreducible elements in Z adjoin I. So what are those elements? They are 1 plus I, which has norm 2. You will see this show up when you factor 2 as an element of Z adjoin I. So what happens is 2 is equal to 1 plus I times 1 minus I. And okay, so why just 1 plus I instead of 1 plus I and 1 minus I? Those are associates. If you multiply 1 plus I times negative I, you get negative I plus negative 1 times I squared, which is 1. So, yep. So really what are we doing is we're coming up with a list of irreducible elements up to associates. So we just have this 1 of norm 2. Then we've already seen that if you have a prime that's 3 mod 4, it's irreducible in Z adjoin I. So this has norm P squared. And then what are all the other irreducibles? They're exactly a plus bi and a minus bi, the distinct irreducible factors of P equals a squared plus b squared, which is this product for the primes P, where P is equivalent to 1 mod 4. So that's the part we still need to show, that when P is equivalent to 1 mod 4, that it really does factor in Z adjoin I. What we need to see is that P equals a squared plus b squared does have an integer solution. In this case, a plus bi and a minus bi, they're not associates anymore, and both have norm P. All right, so before proving the remaining part of this proposition, I first want to talk about a corollary, which is how do you go from knowing which primes are the sum of two squares to knowing which positive integers are the sum of two squares. So let's take a positive integer n, and we'll take its prime factorization. We'll write it as 2 to some power times p1 to a1, p2 to the a2, times pr to the ar, times q1 to the b1, times qs to the bs. where these primes P1 up through PR are going to be distinct primes congruent to 1 mod 4, and Q1 up through QS are distinct primes congruent to 3 mod 4. So given what the statement here looks like, it makes sense that we would separate out the prime factors congruent to 1 mod 4 and the prime factors congruent to 3 mod 4. Well, the statement is n can be written as a sum of two squares. That is, n equals a squared plus b squared for some a and b and z. This has some integer solution if and only if each one of these bi's is even. There's no condition at all on the power of 2 occurring in the factorization or the power of any prime congruent to 1 mod 4. These can be whatever. But if you have a prime factor that is congruent to 3 mod 4, it has to occur an even number of times in the prime factorization of n. Okay, so in this case, where this condition does hold that each one of these primes that is congruent to 3 mod 4 occurs an even number of times in the factorization of n, how many integer solutions are there to n equals a squared plus b squared? Well, that's like asking the number of ways that n can be written as a sum of two squares is 4 times a1 plus 1 times a2 plus 1 times ar plus 1. So you get a factor of 4. Doesn't matter what k is. Doesn't matter what these b1 up through bs, these even exponents are here. But you get a factor of 4 and then times a1 plus 1 times a2 plus 1. You get the product of 1 plus the exponents corresponding to the prime factors that are equivalent to 1 mod 4. Okay, so what I'm going to do is let's assume that we have proven this theorem already, and we know that the last remaining part is to prove the statement that primes congruent to 1 mod 4 can be written as a sum of two squares. Let's suppose that for now, and given that, let's prove this corollary. Let's prove the first part of this corollary about which n can be written as a sum of two squares. So what does it mean for n to be equal to a squared plus b squared? That's the same as saying that the norm of a plus bi is equal to n. So let's take this a plus bi, this is an element of z adjoint I, and write it as a product of irreducible elements in zi. This factorization is unique up to associates because z adjoint I is a UFD. So now we just have to understand which n is the norm of some element in z adjoint I. So let's take our finite product of irreducible elements. Well, what things could occur in this finite product? We're proving a corollary of this proposition 18. And the second part of this proposition gives a complete description of what the irreducible elements in z adjoint I are. And we helpfully noted what all of the norms of those elements are. So we use this description of the irreducible elements in z adjoint I and see that n can only be the norm of an element in z adjoint I if and only if n is a product of a bunch of 2's, because we do have an irreducible element of norm 2, a bunch of primes that are congruent to 1 mod 4, so some primes pi with pi congruent to 1 mod 4. We have, for any prime that is 1 mod 4, we have an irreducible element of that norm, so we could throw that in the factorization. But then we don't have an irreducible element of some norm q, where q is a prime that's congruent to 3 mod 4. There's no element of norm q if q is a prime congruent to 3 mod 4. But we do have an element of norm q squared for any prime q that is 3 mod 4. So we could always get square factors of primes that are congruent to 3 mod 4. So we're allowed to throw in some qj squareds where qj is a prime that is 3 mod 4. So those are the things that we're allowed to combine together in this product of irreducible elements. And so taking norms on both sides, that exactly tells us when n can be written as a sum of two squares. We can have whatever power of 2 we want, whatever power of any prime congruent to 1 mod 4, But if we have a factor of n that is a prime that's congruent to 3 mod 4, it must occur an even number of times, because the only way for that to show up in the norm would be to have that prime show up in this finite list of irreducible elements. And when you take norms, that means that not only does that prime occur as a factor of n, but its square occurs as a factor of n. Okay, so that proves the first part, that the only way that n can be written as the sum of two squares if and only if each one of these bi's in this factorization is even. So I want to give another proof of this that in some sense is simpler, but it certainly is less clear what's going on. Okay, so suppose that a is a sum of two squares, x squared plus y squared, and that b is a sum of two squares, z squared plus d squared, t squared. What I claim is that their product is also a sum of two squares. A times b is a sum of two squares, and we'll see that by actually writing which two squares add up to AB. And it is now a little algebraic exercise to check that AB is equal to xz minus yt squared plus xt plus yz squared. You can check that that works, and that's it. Like, that's all I have to say about this, is it's some algebraic identity that if you have two things that are the sums of two squares, so is their product. Which means now it's enough to just understand which primes can be written as a sum of two squares, because that means if you have 2 as a sum of two squares, any prime congruent to 1 mod 4 is a sum of two squares, and the square of any prime that is 3 mod 4 is a sum of two squares. It is like q squared plus 0 squared. Those are the building blocks of the things that we could multiply together to get the full list of the things that are sums of two squares. So where does this identity come from? It actually does come from factoring in the Gaussian integers, and I'll let you think about the details there. But I have seen this proof written down before in lots of places that once you know the characterization of primes that are sums of two squares, that gives you this characterization of integers that are sums of two squares. But unless you phrase this in terms of irreducibles in z adjoin I and factorizations in z adjoin I, it's totally unclear what's actually going on that makes this identity work. Okay, so I'll pause and erase, and we'll prove this second statement about the number of ways that n can be written as the sum of two squares in the case that all of these exponents for prime factors that are 3 mod 4 are all even. Let's now give the proof of this second part of the corollary that says in the case where each of these bi's, these exponents can corresponding to primes that are 3 mod 4 is even, and n can be written as a sum of two squares, how many ways can n be written as a sum of two squares? So okay, let's assume that b1 up through bs are even. Finding the number of integer solutions, n equals a squared plus b squared, is the same as finding the number of elements in z adjoin I of norm n. Right? If you have an a plus bi that has norm n, you get a solution that looks like this. And if you change that capital A or capital B, you're getting a different solution. You're getting a different way of writing n as a squared plus b squared. Okay, so we know what the irreducible elements in z adjoin I look like. In particular, each prime pi that's congruent to 1 mod 4 factors as a product of two irreducible elements. We'll call them pi I times pi I bar. These are two irreducible elements. Why pi I bar? Because if pi I is a plus bi, pi I bar really is a minus bi, which really is its complex conjugate. So this is like useful notation. So if the norm of a plus bi really is a squared plus b squared is n, then, okay, if we factor a plus bi, we have pi 1 up through pi n. When we're taking the norm of a plus bi is the product of the norms of pi 1 up through pi n, right? The product of the norms on the right-hand side matches this product on the left-hand side. But we know what irreducibles could occur on this right-hand side, and we know what their norms are. There's one irreducible of norm 2, for each prime pi congruent to 1 mod 4, there are these two irreducibles of norm pi, and then there's one irreducible of norm q squared for any prime q congruent to 3 mod 4, that is q itself. So what does that mean? If we know that the product of the norms of the irreducibles over here really is n, then what do we get when we factor a plus bi into a product of irreducibles? Well, okay, I'm going to forget about units for now. If n has a factor of 2 to the k, we need to have exactly k irreducibles of norm 2. And there's this one unique irreducible of norm 2 up to associates, 1 plus I. So that has to occur k times in this factorization. If p1 to the a1 divides n, then we have to have exactly a1 irreducible factors of norm p1. So there are two irreducible factors of norm p1 where this p1 is some prime congruent to 1 mod 4. There's pi1 and pi1 bar. And we can mix and match. We can choose some pi1s and some pi1 bars, but we know that total we have a1 of those things. So let's write this as pi1 to the a11 times pi1 bar to the a12. And what do we know? We know that the sum of these two exponents is exactly a1, and they're both non-negative. Same thing with the irreducible factors of norm p2. Same thing with p3 up through pr, the last of our prime factors of n that's congruent to 1 mod 4. And then if you have some q1 that divides n, where q1 is a prime that's congruent to 3 mod 4, then we know that the number of times it divides n is some even number, b1. So that means that in the factorization of a plus bi, there have to be exactly b1 over 2 irreducibles of norm q1 squared, right? The only irreducibles of norm, the only way to pick up a factor of q1 in the norm is to have an irreducible that has norm q1 squared. And there's this unique irreducible of norm q1 squared, which is the prime integer q1 itself. So, okay, so what are we seeing? We have to have q1 itself showing up b1 over 2 times, and q2 itself showing up b2 over 2 times, and up through qs showing up bs over 2 times. Okay, so by really carefully thinking about what the irreducibles are in z adjoint I, we can see not only, you factor a plus bi as a product of irreducibles, but you can say really precisely what these irreducibles have to look like. Okay, so what are the things that are not determined here? I haven't been careful about units, right? So like these are unique irreducibles up to associates. So there might be maybe this product over here, maybe it's off by -1 or I or something like that. And then we have a choice for each one of these primes that's congruent to 1 mod 4. We have pi I to some power and pi I bar to some power, where those powers add up to the corresponding exponent of pi. Okay, so the number of elements of norm n then is the number of choices we have here. So let me just point out that a11 and a12 are not determined, but their sum is determined. So as soon as you pick a11, it tells you what a12 should be, because they need to add up to a1 together. So ai1 determines ai2. So what could ai1 be? Well, maybe we pick no factors of pi I and all ai factors of pi I bar. Or maybe we pick 1 pi I and we pick ai minus 1 pi I bars. But altogether, we have ai1 is some number between 0 and ai. So how many choices are there here? ai plus 1 choices. Okay, so what is the total number of elements of norm n? What is the total number of choices in this factorization? For each prime pi congruent to 1 mod 4, we get ai plus 1 choices. For all these factors congruent to 3 mod 4, we get no choices at all. And for the power of 2, we also have no choices at all. So the total number of choices is 4 for the units, right? This is just one factorization here, but we could multiply by I, negative I, or negative 1. So there are 4 choices for units, and then times a1 plus 1, a2 plus 1, times ar plus 1. And that is exactly the formula that we were trying to prove. So, okay. What is there to remember about how this corollary actually goes is writing n as the sum of 2 squares is the same thing as finding an element in z adjoint I of norm n. How do you determine all the elements in z adjoint I of norm n? Well, you need a really precise description of what those irreducible elements are in z adjoint I. And we need to know what their norms are, because we know that the product of the norms of all the irreducibles has to be n. So that is the big idea that shows us that the only real choices we have are when we have a prime that's congruent to 1 mod 4 that divides n, we can choose between the 2 distinct irreducibles that have norm equal to that prime.